In this video, we're going to continue our conversation about roots and roots of polynomials. So just a little bit of background. So first we have what's called the fundamental theorem of algebra. Oops. And the fundamental theorem of algebra is that a polynomial um, of degree n has exactly n roots. So, for example, if you have a third order polynomial of um, of a3p cubed plus some a2p squared plus a1p plus a0, and that equals 0, then this is a third order polynomial, and there will be three roots, p1, p2, and p3. You will sometimes have two roots or multiple roots that are equal to each other, and then if you'll recall, that means there's a multiplicity of a root at that number, but there are three roots. And so this is important when we talk about um, higher order differential equations. We'll continue, so this is no longer talking about the fundamental theorem of algebra, but an nth order linear constant coefficient ODE um, will have a characteristic equation which is a polynomial in P, and it's the same order as the ODE. And, oops. So in P, so the characteristic equation has the same order as the ODE. And a characteristic equation with an nth order um, an nth order ODE with n roots will have n independent functions that make up the solution. Um, where you have c to the n e to the p n times t plus all the way down to c1 e to the p1 times t. And one helpful rule for starting to think about these roots, starting to think about how these roots tell us about the stability and behavior of systems, we're going to introduce a necessary but not sufficient condition for a polynomial to have negative roots And this matters to us because that means the system is stable. So the necessary but not sufficient for all roots of the polynomial condition to be negative means that all coefficients of the polynomial, well, this condition is that all coefficients are positive. So what does this mean? So if you see a polynomial, for example, 2p squared plus 5p minus 6 equals 0, because it's a necessary condition for stability that all of these coefficients are positive, this coefficient of negative 6 here means that this polynomial is going to have at least one positive root and the system is going to be unstable. So for first order polynomials, we have a few examples. If we have p plus 9 equals 0, then that means that p is equal to negative 9. And if this were the characteristic equation of a first order ODE, then this system is stable. If you have p minus 9 equals 0, then the root p is equal to positive 9, and that system is unstable. And so in general, if you have p plus a equals 0, then p is greater than 0 if a is less than 0. Meaning, if a is negative, then p is going to be positive, the root is positive, that's unstable if p is greater than 0. And there are examples also in the book for quadratic and even for cubic for third order polynomials. We'll go ahead and stop there and take a break before the next video.